So, just quick once over, I changed the picture of the office hours of my class schedule on the front page of Canvas, so when you need to figure out where's my office hours, every day of the week, 7:30 to 8:20. If for some reason there's something not at that time you can't make it, email me, and if there's some other way to figure out a different time or different place on campus we can meet, that's fine. But you gotta let me know. Or if there's an issue that maybe we have to do a Zoom some other time, it will work out for both of us, let's see what happens. But outside of that, we do a lot of work in here. But it can't stay silent. If you have a question, you have to ask. Interrupt. Interrupt. So when I say, are there any questions? That's your cue. Or if I haven't said that, interrupt. Okay? And like I told you, the only other place you're going to have to worry about things is in the announcements. And that's where I put, you're not going to see this. You're only going to see office hour and chapter 10A notes that posted. That's not going to be you yet. That's chapter 1 summary and review. That's delayed until time for that. So ignore the you know that. I don't put anything in the assignments. I do not do grades on Canvas. You'll never see anything there. I do grades in my own grade book. But when it comes time for grades, you will get a grade printout after every test. It's not going to change in between tests a whole lot. There might be some quizzes, 1 or 2 quizzes. I'm not going to check homework until the day of the test, so that's not going to change your grading. But for any reason, if you have a question about your grade in between, yes, print out your grade. Okay, but I'm going to give you a printout after every test with everything on it, so you can double check and make sure everything's right. Every now and then, the fat fingers might match on the wrong number. Okay. Okay. Sometimes there might be something on Pearson, like a quiz on Pearson. I even put a test on Pearson. Okay. When I put something on Pearson, what I tend to do is I would give you until 11:59 that night, but it's usually timed. So it would be under the same relative time frame. What I always do is I give you a practice test that's not like the test, but kind of, so you get the feel of how answering questions look like. Because on homework, you can go backwards and forwards and redo problems and things like that, but not on tests. On tests, once you finish problem number 1, you can't go back to number 1. Once you open up question number 2, you have to do question number 2. But if you need to stop, all of a sudden, maybe, the dog just threw up. You got to take care of it. So you got to stop the test. Well, if you go to question 3, you now have to do question 3. But if you hit, save my work, I'll come back before you open up question 3. You did question 2. And don't go on to 3. It'll stop right there, and you can pick up a question 3. Okay? And that's something I would show you before I would have you do something. I always like to give you a dry run without any penalty, without any bearing on your grade, so you can actually get used to it before it has to. Okay. Segmentation, numbers. In general, two ways to think about the counting numbers. The counting number is just a list. It's a list of things, a list of numbers. It's a set of names in some kind of order. What's the order? For some reason, we put them in the order of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just like for some reason, somebody put the alphabet in that 1, H, C, E, F, G. Is it arbitrary? Who put the alphabet in that order? Was it because of the song? Well, the alphabet's in some kind of order. Why does Z have to go last? That's not fair to the people whose last name begins with Z and do it alphabetically. You have to multiply. And she took away that. Well, counting numbers has telling how many. How many is. So counting numbers is a list of things. There's all the counting numbers. Look the numbers. But it also can tell us a quantity. How many of us? Quantity. So here's our big $10 words for the day. Cardinality. Cardinality. This is going to be on the final. Everything we do is on the final. Everything final's cumulative. Well, what does that mean? It means everything we do, you need to know in December. You're still doing addition and subtraction, right? Your entire math life is a big cumulative. Cardinality of a set. The cardinality of a set is the number of elements in the set. It's just how many do you have? That's what cardinality means. How many are there in that set? The cardinality of set A is denoted as. So you have set A is equal to some set of stuff. And the cardinality of set A looks like this. That's an N. Cardinality of set A. And then you have the cardinal or set B that's got some other stuff in it. And then if we want the cardinality of set B, I don't do lowercase anyway. The cardinality of set B would just be N parentheses set B. How many elements are in set B? How many things are there? Set C. Let's do this. First, we put some stuff. So the cardinality of set C so set C is the set that contains circle, rectangle, triangle, square. So the cardinality of set C is what? 4. Because how many items are in set C? There's 4 items. There's 4 things in it. That's what cardinality means. How many are in it? The cardinality of set is the number of elements in the set. How many things are in that set? No, reject. Back to the- All right. Reading. Things that makes a math teacher valuable is the fact that students can't read a map. Because teachers or mathematicians that write math books, they write it in a language that's not decipherable to students. You need an expert to decipher it for you. Because they're using all these strange symbols and they never explain what these symbols are. Case in point, A equals set X, there's a line X, and then there's that crazy looking thing. We learned that's the natural numbers, and -7, and we know that's a inequality, but I don't remember if it's less than or greater than, if that's got an equals, and then we pose the set. I got a lot of stuff there, but what does it all mean? So I'm just going to take a little segue, sidestep, and just show you something that I experienced, because if still back into my own teaching, experience helps you become a better teacher. The first day of calculus when I was at UCLA trying to be an engineer, Professor Raymond or Dr. Raymond Redheffer, okay, classroom or lecture hall about 400. He puts up the formal definition of a limit. Just a bunch of snot-nosed 17, 18-year-olds. It's like, what we're looking at each other, we don't have to prove. And then he reads it to us. For every epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of x minus L is less than epsilon. Whenever 0 is less than the absolute value of x minus c equals less than delta, means the limit of x squared to c of x equal to. Again, I can remember 41 years ago a lot better than that. Mathematically speaking, that is the precise definition of it. Exactly. Takes away all the ambiguity. That's how mathematicians speak. That's how they write. We have to interpret. Okay. That means when a function in the x value get really close to this number, the y value get really close to that number, and that's all it means. That's what it means. When x's get this really close, y's get really close up there. So, well, in mathematics, what is getting really close to? That's where it all comes in. And this is out of the 1700 by a mathematician by the name of Dustin will be coaching. I even talked with another professor that named his dog Coach. That's the nerd and all. Well, not all. Well, maybe. So you need to be able, because I don't know how far you're going to go. We never know. Decipher this language. And these are not too bad to really work with. Set A. So we're defining what say is comprised of. Set A is equal to. It's telling us what's in it. Like right here, I told you what is equal or what is in set C. C is equal to this stuff. Set A is equal to X, all the values of X, such that X, this symbol, means belongs to. That's a symbol for belongs to. So it's equal to a whole bunch of different values of X. X is a variable, can be anything we want to make it. And those X's belong to the set of natural numbers. So we're only talking about natural numbers. But we're not talking about all the natural numbers. Only a very specified amount of them. And I don't want to have to write them all out. That's the whole point. It's a set of natural numbers, and the X's are -7 is less than or equal to the X's, which is less than 9. All of the X's are between -7 or equal to -7 and less than 9. So they're natural numbers and they're between here and here. That's the definition of what's in that set. It's describing what's in the set without writing it out for you. So A is the name of the set. This is the name. Set A. It can be any letter of the alphabet and is usually typically capitalized. E is the equal sign. When you read it out loud, A is or A is equal to. A is a set of. The left brace is read aloud as the set of all. A is equal to the set of all, the set of all. That's how we begin from left to right. X is a placeholder, a variable, to represent an unknown or basically all the possible values that are in the set. And you got to think about how math changed for you when you went from arithmetic into algebra. And all of a sudden they put letters in the math. I freaked out when I was a freshman in high school. I was a straight A math student from all the way through the 8th grade. Then I went into honors algebra. So freshman in high school. Why? Because all I had were A's in all my, first through 8th grade. So you must be ready to go into honors algebra. And I got a D. So I'm sitting there going, what's the alphabet doing in math? What am I supposed to do with this? And it didn't make any sense. I did not understand the concept. I raised it up to a C, but then I dropped out of the honors program my freshman year. Went to regular young. Thank God I did not give my brothers a D. Because my friend would call him Mr. Somonix. Somonix is something to take closely. But if you ask them about the basketball game that last weekend, then we'll just go on to that. I got a guy that would jump up on the table and pretend he was Pete Townsend from the hood. That was Until you got fired. Private education, you pay for it. Anyway. X is just all the possible values that you might want to plug in. X and anything like, it's just a variable, a letter that can change based upon some kind of. That's all. It's an unknown number. The vertical line is read aloud as such that. So the set A is equal to the set of all x's, and then this is such that. This vertical line is such. So now they're giving us the rule, the set of all x's such that this symbol means is an element of or belongs to it belongs to, it's an element of, it's part of the x's that elements of or elements that belong to. The elements that belong to and that n is the natural number. The set of natural numbers. When you put it all together, set A is a set of all x's such that x belongs to or is an element of the natural numbers and -7 is less than or equal to x, which is less than 9. All right, there we go. Let's read this out loud together. Because if you cannot read it yourself, it's not going to stick. There we go. Set A is equal to the set of all x's such that x belongs to the natural numbers and -7 is less than or equal to x, which is less than 9. Is a set of all numbers such that each number is an element of the naturals and is between -7 and 9, including -7, but not. So here's our first example. We want the cardinality of that set that was just given to us. So we want the cardinality of the set. Yeah, lowercase n. Sometimes it's not going to be incredibly, right in front of your nose. You got to actually make it write it up. So it's a set of all x's such that it's got to be a natural number, and -7 is less than or equal to x, which is less than 9. Those are the restrictions. So it's got to be a natural number. So natural numbers start with what? The natural numbers start with what? 1. So 1, 2, 3, 4 goes on through. And then you have this restriction. -7 is less than or equal to x, which is less than 9. So that means it would be -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. Do I put 9? No. I stop with 8 because there's no equals on the 9. So is it all of that stuff? No. And the key is in the word and. It's got to make this true. That part has to be true. Not spell the word true. That part's got to be true. And at the same time, this part has to be true. If it's only this part, then it would be an infinite number of numbers because there's an infinite number of natural numbers. But we only want the natural numbers that are between -7 and 9, including -7. So here's all the naturals. The answer would be infinity. But we also have this to take care of. So do all of these count? So what do we eliminate? The negative, and who else? The 0. So the only numbers that satisfy natural and between -7 and 9 are these numbers right here. The answer is how many numbers are right there? 1, 2, 3, 4, 5, 6, 7, there's 8 numbers. So the cardinality is 8. How many elements are being described in that set? There's 8 in that set. But you have to decipher how it's being described. You're given clues. Set B is equal to the set of all x's where x belongs to the set of natural numbers and x minus 5 times x plus 10 equals 0. So now it's going to invoke a little bit of algebra 1. Some of you might have taken algebra 1 10 years ago or longer. Hey, you know what? I took algebra 1 45 years ago. So I win. I'm sorry. I guess it's like a reflection of my age a lot. I noticed this in the last 3 semesters. That's because I'm old. My wife turned 60. I'm 59. She turned 60. My kids are 35 and 30. It's about I outlived some of my favorite rock stars. The manager of the Dodgers is younger than me. That was the real. Anyway. So the cardinality of set B is equal to all the natural numbers. So we're talking about a whole bunch of, an infinite number of numbers. That's an infinity of them, but it's got to make this, the word and, it's got to solve both. So, little algebra. Anybody remember how to solve something that looks like that? Something called like a quadratic equation? Let me start you with this. If I gave you x plus 3 equals 5, how do you solve that? Subtract x equals 2. Plug it in 2 plus 3. If I gave you 4 times x equals 64, what would you do there? Divide both sides by 4. Undo multiplication by division. So x is equal to 16. If I gave you 9 times x plus 27 equals 0. We want to isolate the multiplication, isolate the x term. So we're going to undo the addition by subtracting 27 from both sides. So now we have 9 times x, and over here, negative 27. So now it's just multiplication. Divide both sides by 9. Negative 27 divided by 9 is negative 3. 9 times negative 3, that's negative 27, plus a positive 27 makes 0. Undo, basically, solving an equation is this phrase. You undo what's being done. To solve for x, you want to undo what's being done. If there's addition, you subtract from those. There's subtraction, you add to most. Multiplication, you divide. Division, we multiply. And now we look at this. There's a little something in algebra called the zero product problem. And this is where a teacher might say, you're supposed to know this already. And I don't say that. I'm trying to help remind you. And if it doesn't click, then try to teach it. The zero product property says, if you have a product of 2 things, 2 factors, A times B, and it equals 0, you multiply any 2 things together and it equals 0, then A has to equal 0 or the B has to equal 0. The only way you can multiply 2 things together and get 0 is because one of them has to be the 0. That's the only way we're going to get 0. Does that make sense? If you had 9 times y equals 0, well, the only way we can multiply 9 times something and make 0 is because y is equal to 0. Okay? You divide both sides by 9. Zero divided by 9. 9 goes into 0, 0 times. So over there, we have a product. We have this x minus 5 times this x plus 10. We have multiplication. And it's equal to 0. So the only way these two can multiply together and equal 0 is if this x minus 5 is 0, if this is equal to 0, or if this x plus 10 is 0. Those are my two factors. So you let the two factors equal 0. And then to solve for x, we would add 5 here. And this x is equal to positive 5. We subtract 10 over here. This x is negative 10. So for x minus 5 times x plus 10, there are two solutions. If you plug in 5 minus 5 times 5 plus 10, 0 times 15 makes 0. It works. So I plug in 5 for x. If you plug in negative 10 minus 5, negative 10 plus 10, this is negative 15 times 0. Negative 15 times 0, I get 0. So negative 10 is a solution. So this has two answers. It's got to be a natural number, and it's got to be a solution to this. So what is the cardinality? Set B. Good. What? And that's where it gets a little frustrating. Because you do all that work to figure out what's in the set, and that has absolutely nothing to do with what the answer is that you put for the question. Because the question is, how many items are in the set of B? Now, what are the items in set B? Because it's going to be very tempting to put, well, 5 works. Negative 10 is not a natural, so that's a no. 5 is a natural, so I put 5. Because that's the only number that is natural and a solution. I'll put 5. But 5 is what, that's the number that's in the set, but how many things are in the set? There's only one item in the set. And that's the question of cardinality. How many are back that up and just this question actually would probably come from this kind of a problem. You wouldn't see this, you would see it would start here in an algebra class. And you would be told, solve the question by factoring it or quadratic formula or completing the square. Then you would factor it to this, and you let each factor equal 0. A little more straightforward. Set C. Set C is a set of all x's such that x is a natural number. 10 is less than or equal to x, which is less than or equal to 50. And x is divisible by 5. So we have three restrictions on what's in set C. It's got to be natural. So starting from 1 going to infinity. It's got to be natural. So 1, 2, 3, going forever. It's got to be between 10 and 50. So that means you can start at 10, 11, 12, 13, and it's got to go all the way to stop at 50. But then it has to be divisible by 5. So we're only going to use the ones that are divisible by 5. So in the list of numbers from 10 to 50, who's divisible by 5? What's the rule for divisibility by 5? And so what we look for, end in a 5 or 0. If it ends in a 5 or a 0, it divides by 5. So because it has an equals on the 10, 10, 15, 20, 25, 30, 35, 40, 45, and there's an equals on the 50, so 50 counts. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. The cardinality of set C is equal to breaking it down one thing at a time. It's a natural number. Okay, what numbers am I thinking about? 1 to infinity. Then in between 10 to 50. Okay, it narrows my search. Then only the ones divisible by 5. These are word problems, and the biggest problem with word problems is nobody wants to do them. Because you read the word problem and you think you're supposed to come up with an answer out of the top of your head. You're supposed to like automatically think, oh, the answer's done. It's not going to work that way. Break it down, please, by please. Maybe write it out. You actually would get more points when you write it out than just coming up with an answer. Not extra credit, I'm talking about partial credit. I'm going to leave that one, and we'll talk about that one for extra, no, some extra credit question maybe on that. So look at this one right here. And give it a try. This is B on the note page. We'll discuss it next Tuesday. We're not leaving, we're not done, close to being done. But I want you to highlight this, and we're going to look at that as possible bonus on your test. What is the cardinality of that set? Do myself a little note here. So going back to the rabbits. one-to-one correspondence. Process of counting the objects in a set connects to the process of counting the object in a set connects the list view of the counting numbers with cardinality. So list of things and then how many things are in the set. As adults, this connection is so familiar that we're usually not even aware of it. I'm trying to think about how in the world would I explain why we count? What do you mean? We just count. It's in our nature. Was it real? But for young children, this connection is not obvious, and grasping it is an important milestone. One of the reasons the concept is difficult is because when we count a set of objects individually, we are making one-to-one correspondence between an initial portion of the list of counting numbers from a set. A one-to-one correspondence. One rock, one rat. One rock, one person in the tribe. Correspondence. One number to one person in the tribe, that's a one-to-one correspondence. Side note. Who has kids? Or little brothers, who has family that are young? You want them to do well in math. Then never, ever, ever badmouth math when you're young. Never say that it's hard. Because children are always looking for the easy way out. And come on, think about it. Think about yourself. You look for the easy way out. And if you go home and say, oh, math is so hard, I'm not very good at it, nobody in the family is ever good at it, then they'll just say it too. That's giving them a get out of jail free card. I must not be good at it either. Okay, don't let them off the hook. Second, be encouraging with, you don't have to like go home and, oh, math. You don't need to do that. But you can be a little more positive about, well, look at what I've learned today in terms of a type. Maybe there's something you get somewhere that you never noticed. Third, when we're dealing with kids, some of the best ways to learn math better is to put a musical instrument in their hand. Some of the better math students that I've ever taught were able to count because of music, especially with fractions, when they learn notes. And it's, again, for me, it started during COVID. I started watching all of these first time reaction videos on YouTube because I'm watching my older music being listened to for the first time by people who never heard that kind of music. And they're just never realized that bands actually played instruments. What's this used? And I was watching somebody listening to Rush for the very first time. And the complexity of the count in that music. And how complex it was. They're just three guys. Or the complexity in Santana doing Woodstock in 1969. And they were high as a kite. Because they took really bad acid. Well, they did take bad acid. But they took acid too close to when they were supposed to walk. They thought they had like 7 hours before they were going on. They were going on, they were told, in the next 2 hours. And so, wait a second, what do you mean? But they were the headline, they brought down the house. Well, they brought down the field. At Woodstock. The most memorable act of Woodstock. It changes how the brain will think, not the acid, but the music. Being able to count, to play an instrument. So you can get your child or your little brother and sister to start seeing. I have no musical talent whatsoever. I've never played music. My kids did a little bit. I wish we would have pushed them a little bit further. But if you can't, give them every opportunity. Even if it's just watching videos and just sitting here, watch how this counts. Take a look through the simplest version. All you gotta do is do a search on YouTube. I know it's like saying use this multimedia device, but when you get stuck on something and you don't know how to do something, there are hundreds of thousands of people who have an answer, and it's a free place to go find something that everybody has an opinion on. When I don't know how to do something, I can find a video for somebody to show me how to do something. And if I don't like them, I just find somebody else. When you can't understand something that's being taught in here, you can find another video of somebody you can do it. But music can help. So we're not aware of it. But for young children, the connection is not obvious. Grasping it is an important milestone. One of the reasons this concept is difficult is because when we count a set of objects individually, we're making one-to-one correspondence to complete an initial portion of the list and the counting number within the set. One-to-one. A one-to-one correspondence between two sets is when elements of one set can be paired exactly with one element from another set. Exactly. That means one element here has one element there. Okay, exactly. Not two elements, but there's one element. Can the following sets be placed in a one-to-one correspondence? If so, give an example of one such correspondence. So 1, 2, 3, 4, 5, A, B, C, D, E. How many elements from set B? How many? How many elements? What's the final element? 5. So you have 5 elements here. You have 5 elements here. Can every element here match up with exactly one element there? Yes. So this is an example. You can make a one-to-one correspondence. So give an example of one such correspondence. So we would write it like this. You can just go straight down. 1A, 2B, 3C, 4D, 5E. Does it have to go like that? No. We could have gone 1B, 2C, 3D, 4E, and then 5A. But every element in the first set matches up with exactly one element in the second set. One-to-one correspondence. There's no specific order involved, like you're going to see in the next one. I'm going. So part B. Can I make a one-to-one correspondence of a set A and set B? No. Because the cardinality of set A has three elements, and the cardinality of set B, there are four elements. So I can go 4 diamond, 8 club, 10 heart, and I can't make a one-to-one with the spade. There's going to be somebody left out in set B. So it's not going to be a one-to-one. For every one element here, there's exactly one element that one-to-one. From here, we're going to look at the homework. Because this is where we get some questions regarding. So on the assignments, this homework practice is due the 18th. And that's just familiarizing yourself with how to do stuff on Pearson. So that's due the 18th. That's next Tuesday. But here's the homework itself, section 1.1. This format, they choose the format over some. So I'm going to get started. And I want to show you, I don't know if I did with it there or not. So, click on that, it gets show me the textbook where this is at, ask the publisher. This is the list of questions. So this is question 1, question 2. I can expand it over here and go to the questions. But if see if I have a question. Because you're supposed to be able to print them. Option was right here. But I'm gonna have to really look at this because they changed the format anyway. You should be able to, and I will make sure I double check and find out what that is going on, but printing out the homework would look like this, so you don't have to sit there in front of the computer and do it all. You do it on paper. You're not turning it in like that, but you're doing it on paper, and then you go back in and type in your hand. Okay. Now, said and done, let's go back to that thing. Sorry about that. But I want to make sure we have option. It's supposed to be there in the sign. So, which of the following statements about this child's counting strategy is correct? One, two, three, 5, 9, 10, 7, 28. There's our process. The list of counting numbers is not an ordered list. There is one-to-one correspondence, and the last number indicates the cardinality of the set. That's why we're close. There we go. The list of counting numbers is not an ordered list. The list of counting numbers, 1, 2, 3, is not an ordered list. There is one-to-one correspondence, and the last number does not indicate cardinality. Okay, I have no idea if that means anything. I don't think that's it. The list of counting numbers is not an ordered list. There is no one-to-one correspondence. And the last number indicates the cardinality of the set. 1, 2, 3, 5, 9, 10, 7, 28. The list of counting numbers. So here's the counting numbers. Is not an ordered list. So it's not in order. There is no one-to-one correspondence. I guess between here and the seashell. And the last number indicates the cardinality of the set. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them. The list of counting numbers is not an ordered set, ordered list. There is one-to-one correspondence, and the last number indicates the cardinality of the set. The list of counting numbers is an ordered list. It's not an order. There is one-to-one correspondence, and the last number indicates the cardinality of this set. Does not indicate the cardinality. There's 9 things. All 3 of these says it does indicate the cardinality. It's not an ordered list, but it is a one-to-one correspondence. It's not in order. It is one-to-one for every number here. There's a T-shell, and that is not the cardinality. Right. Now, this homework on this other version is going to be a different number. That's me. Check in. Fantastic. Any question about that one? You have to read through every single one because it was one tiny thing. Another one like it. You see how we have some missing things? Is it 1-to-1? Well, that would be a clue. Which of these sets can be placed in a 1-to-1 correspondence? So here's a set 1, 2, 3, 4, 5, MNOCR. Can I put this set and this set in a 1-to-1 correspondence? Is there exactly one element in this set to match up with one element in that set? Yep, so that could be a 1-to-1 correspondence. D, can this be CR1M with CTW? No. So that's a no. How about ABC all the way stops at F and 4, 8, 12 stops at 1? So yes, so this goes, A, B, C, D, A, B, C, D, E, F, that's 5 elements, right? And if you go 4, 8, 12, 16, 20, that's also 5 elements. So there's 5 elements here and 5 elements here. You can do a 1-to-1 correspondence. T is a letter in this word jar. And you have the numbers 1 through 4. Well, is T a letter in that word? So there's 0 here, and you have 4 things there, you're not going to get 1-to-1. I take that back. I'm reading this wrong. The answer is correct, but I'm reading wrong. I didn't read it from left to right. The set of all T's such that T is one of these letters. And there's only 3 letters. So there's only 3 elements in this one, and there's 4 elements there. So you have 3 and you have 4. There's not enough to make a 1-to-1. So that's it. You got a square and that's a gamma. Gamma or lambda. Anyway, you have an upside down triangle. 2 elements, is that going to be 1-to-1? So the answer would be A, C, and T. You would want to check all that apply. They break it down. And the first one, the answer yes. Check answer. Nice work. The second one, no. Check answer. Excellent. This one, yes. Check answer again. Well, 6. Oh, I lost the finger. Yeah. Then you can hit try again. You unlimited try. I know it says 1 try left, but if you don't do it on that try because it's multiple choice, you would have to do the whole question over. This will go. Now look at my homework. So when I go back to this, it shows that 1.12 is not. It shows right here. I completed number 1.1. I haven't done or started 1.2, but I have a check and an X because I got one part of 1.3 wrong. So I gotta go back and fix that. Get your Pearson going. Make sure you do the homework. That's just the practice one because that's due on Tuesday. Download the notes. I got the roll taken because I counted. Same number that was here in the morning. So everybody's here. And we'll see you on Tuesday. Have a nice weekend.